Okay, class, so we're done with mass transfer for flow on a flat surface. And that's the first of the three geometries that we're going to tackle on mass transfer coefficients in various geometry. So this is the second to the last. Now, for flow past single spheres and for very low Reynolds number, where V is the average velocity in the empty test section before the sphere, the Sherwood number, which is, as we have learned, is K sub C prime D sub P, that's the diameter of the particle, divided by the molar diffusivity should approach a value of 2.0. Now, our molar flux in this case, for this scenario wherein we have a laminar flow and our Sherwood number approaches a value of 2.0, is given by 2 dA sub B, or D subscript AB, divided by the diameter of the particle times the difference in the concentration of A from 0.1 to 0.2. Now, as you can see, the K sub C here is comparable to the expression 2 D sub AB dP. And if we have a dilute solution, and most of the case our solution is dilute, our K sub C is K sub C prime as well, as of them I have already illustrated in the other sample problem. So we can say that our K sub C here, which is K sub C prime, is equal to 2 D sub AB dP. Now, if we will rearrange and we will use that particular scenario that says that if it's Reynolds number very low, then the Sherwood number could be equated to 2, so we will have this expression anymore. However, we have to take note that as our flow deviates from the laminar profile, then we will be a marked increase in the K sub C prime, because this particular relationship is for low Reynolds number. Now, for gases, so this is specifically for gases, if we have predetermined the Smith number and its value falls on the range of 0.6 to 2.7, and also we have predetermined our Reynolds number and it falls on the value 1 to 48,000, the Sherwood number, appropriate Sherwood number expression that we will replace in lieu of this is 2 plus 0.552 times the Reynolds number raised to 0.53 times the Smith number raised to 1/3. That is if we're talking about a gas. Now, this same equation also holds for heat transfer problem where our Prandtl number replaces the Smith number. So in lieu of the Smith number here, it will be now our Prandtl number. And the Nusselt number H dP over K replaces the Sherwood number. So if you recall, in our convective mass transfer, we have discussed about the Nusselt number and how does it point us to the heat transfer coefficient, which is the H. In our case here, we are determining the K sub C, or the K, specifically our mass transfer coefficient. Now, the expression that you have again here on top is for gases only. The last two in here are for liquids. So for liquids in which the Reynolds number fall on the range 2 to 2,000, this will be the appropriate Sherwood expression. And for liquids whose Reynolds number fall higher than this one, so it's 2,000 to 17,000, this would be our Sherwood number. Why do we need to have an expression for the Sherwood number? Because as you could see here on top, our Sherwood number, which is not equal to 2 if it's not anymore very low or laminar, will be equated to K sub C prime D sub P over DAB. For us to know our convective mass transfer coefficient, and if we know this, then we can determine our flux, just like how we do it in our heat transfer problems. Then we have to determine the heat transfer coefficient, and before that we need to know the appropriate dimensionless number to use. And once we have already the H, our convective heat transfer coefficient, we can substitute it to our heat flux. In here we have the flux or the molar flux because we're talking about mass transfer. So these scenarios wherein we're using the Sherwood number is for flow past spheres. Okay, now To illustrate the use of the formula and how we choose the appropriate formula for the problem, we have this second to the last sample problem. Here you are asked to calculate the value of the mass transfer coefficient and the flux for mass transfer from a sphere of naphthalene in air. So your sphere is in air at 45 degrees Celsius and 180 m, and air is flowing at a velocity of 0.305 meters per second. The diameter of the sphere is given to be 25.4 millimeters. The diffusivity of naphthalene in air at 45 is given to be 6.92 times 10 raised to negative 6 meters squared per second. And the vapor pressure of solid naphthalene is 0.555 millimeters mercury. Now the problem is asking for you to determine the two required information, the mass transfer coefficient and the flux, both on SI and English units. So just for illustration purposes, I will limit the discussion of finding the two unknown required information here using SI units. I leave to you the procedure on how to find these two using English units. So just like how we start with a particular problem, we need to go to our board and write the scenario that will illustrate the problem. So this is our second problem under convective mass transfer coefficients in various geometries. So our problem talks about a sphere suspended in air. So this is our naphthalene. So I'll just place here naphthalene, our sphere naphthalene, and it's suspended in air. So air is flowing in our naphthalene. Our air is at 180 m, 45 degrees Celsius. Okay. Now, the velocity of air is also given to be 0.305 meters per second. And we're given the naphthalene diameter, that's the particle, which is 0.0254. And the diffusivity at 45 degrees Celsius is 6.92 times 10 raised to negative 6 meters squared per second. And when we speak of A, that's our naphthalene. And our B in this case is air. Okay? Now the vapor pressure on the surface of naphthalene, because your naphthalene will diffuse in air in all direction, that is, its vapor pressure, which is also equal to its partial pressure, is 0.555 millimeters mercury. If this is converted to Pascal, that way we will have already just substitution later on for SI set of units. This will be 74 Pascal. Now this is the given information for our problem, and the required information are the mass transfer coefficient, and we have the flux. Okay, these are the two. Now if we go to the solution to this, since we are after for the mass transfer coefficient, we are to know that when we speak of gases, our convective mass transfer coefficient will have a subscript of G, and our G or our K sub G prime will be equivalent to K sub C. That is if it's in terms of concentration, and we will need to divide it by RT so that we'll have it expressed in terms of K sub G prime. Now for dilute solutions, your Sherwood number, which we have read just a while ago, is K sub C D sub P over the molar diffusivity. Okay. Now, if I want the K sub G prime, I need to determine the K sub C prime. This is one of my unknowns. I need to find this, so I need to determine the K sub C prime. which is just equal to K sub C for dilute solutions. We have already explained that in several sample problems. So these two are just the same. So if I have this, then I will have the K sub G. So I will have this in mind, the formula that will convert from K sub C prime to K sub G prime. Now the next thing that I will do, since I have already the Sherwood expression here, that would lead me to the K sub C, which is just equal to my K sub C prime. Then I need to determine what Sherwood number I will equate to this particular Sherwood number expression, knowing the D sub P and the D sub AB already, because these two are given in the problem. Then I get to know the K sub C. Now from what we have read in the previous slide, we have to choose from the appropriate expression the formula for the Sherwood number based on the value of the Reynolds number and the Smith number. So we need to establish, in this case, our velocity profile. So we can start with our Smith number. So we have mu divided by rho and the molar diffusivity. In this case, we have a dilute solution, so we will be getting the mu, the rho, and the DAB, and we'll be basing it on air. So for air, at 45 degrees Celsius, your mu is equal to 1.93 times 10 raised to negative 5 Pascal seconds. Density is 1.113 kilogram per cubic meter. So with these two taken from the appropriate property table and the given DAB in the problem, we can determine our Smith number. So our Smith number upon substitution would be 1.93 times 10 raised to negative 5. That's the one that we have here for the mu. And divided by 1.113, this is our density, and 6.92 times 10 raised to negative 6, which is our molar diffusivity. This will give us a Smith number of 2.505. Now for the Reynolds number, so take note that we have a case here of naphthalene in air. So we will choose from the Sherwood expression the appropriate formula. So our Reynolds number is, of course, the diameter, the density, and the velocity divided by the mu. And if I will substitute the value, so the diameter in this case is 0.0254, the velocity is 0.305, and we have the density, which is 1.113, and the mu, which is 1.93 times 10 raised to negative 5. This will give me a Reynolds number of 446. Upon substitution, we will have a number of 446, or a value of 446 for the Reynolds number. So if we will go back to our slide later, I'll show to you later, for a Smith number on the range of 0.6 to 2.7, the appropriate Sherwood expression is 2 plus 0.552 multiplied to the Reynolds number raised to 0.53 multiplied to the Smith number raised to 0.33. Now, where was this taken from? Okay, we'll go back to our slide. So remember this, a 2.505 for the Smith number. And we're talking about gases. So I'd like to go back to our slide. Now, these two, the last two are for liquid, so we will not look into them. We will just have this one. So for gases, for Smith number on the range 0.6 to 2.7, our value for the Smith number, by the way, is 2.505. So it's within this range. And a Reynolds number of 1 to 48,000. Our Reynolds number is 446. So we are falling on this particular values of the Smith number and the Reynolds number. So we'll be using this particular formula. And that's the formula that we did use here when we solve already for the Sherwood number. So this is the formula that we will use. So if we will substitute values here for the Sherwood number, like 2 plus 0.552, the Reynolds number, which is 446, which is raised to 0.53, the Smith number, which is 2.505, raised to 0.33, our Sherwood number here will be 21. This is our Sherwood number, and this same Sherwood number of 21 will be the one that will be equated to this particular equation. So let's say we'll have this as equation 2 because I already set this as equation 1. So equating 2 to our value. So from 2, so we have 21.0 equal to K sub C. The diameter is 0.0254, and we have the molar diffusivity of 6.92 times 10 raised to negative 6. This gives us a Kc value of 5.72 times 10 raised to negative 3 meters per second. Dilute, our solution is dilute, so this is the same K sub C prime. So our requirement is we will determine the K sub G prime. That would be our K sub C prime over RT. So we will use this 5.72 times 10 raised to negative 3. We will divide it by 8.314, and our absolute temperature of 45 degrees Celsius will be 318 in this case. So we have a K sub G, which is equal to 2.163 times 10 raised to negative 9. So this is kilomole A, our naphthalene, per second per meter squared, and we have this in Pascal also. So this is our K sub G prime. Our K sub G and our K sub G prime are just the same because we have a dilute solution. And by the way, this is already our K sub G. Okay? K sub G and K sub G prime are just the same because we have a dilute solution. So K sub G. The next unknown is the flux. So our N sub A is actually K sub G times PA1 minus PA2. So a substitution of the known values that are determined and given in the problem. So this 2.163 times 10 raised to negative 9 we will multiply it to partial pressure at point 1 is 74 Pascal, and partial pressure on point 2, which is all air, is 0. Although actually it's not 0, but it's very near 0 because it's very dilute. So your molar flux here is 1.599 times 10 raised to negative 7 kilomole naphthalene per second per meter squared. So this is how we find the two required information. We determine the appropriate Sherwood expression that we will equate to the Sherwood value that is given, and that is K sub C, D sub P, DAB. So this is generally our Sherwood number. So we will just look for an expression to equate to this so that we will find the appropriate convective mass transfer coefficient.